The Sanford Underground Research Facility, or SURF, is America's deep underground science laboratory. Our mission is to advance world-class science and inspire learning across generations. SURF hosts cutting-edge research in multiple disciplines, including physics, geology, biology, engineering, and more. Work at SURF is contributing to the fundamental understanding of our universe, advancing our nation's energy independence, exploring life in extreme environments, and providing basic research that is the foundation for ongoing technological advancement around the world. SURF's collaborators include over 2,000 scientists from more than 200 national laboratories, institutions, and universities worldwide. SURF also plays a vital role in inspiring the next generation of STEM professionals with a robust education and outreach program that reaches nearly 20,000 students and 400 teachers annually. SURF is generating a $2 billion economic impact on South Dakota this decade alone, with the potential to create 1,200 jobs across the state. We are proud of our history, which includes Nobel Prize-winning research on this site, and we have a bright future with ongoing and planned experiments that will continue to inspire and push the boundaries of human knowledge for decades to come. The Sanford Underground Research Facility, or SURF, is America's deep underground science laboratory. Our mission is to advance world-class science and inspire learning across generations. SURF hosts cutting-edge research in multiple disciplines, including physics, geology, biology, engineering, and more. Work at SURF is contributing to the fundamental understanding of our universe, advancing our nation's energy independence, exploring life in extreme environments, and providing basic research that is the foundation for ongoing technological advancement around the world. SURF's collaborators include over 2,000 scientists from more than 200 national laboratories, institutions, and universities worldwide. SURF also plays a vital role in inspiring the next generation of STEM professionals with a robust education and outreach program that reaches nearly 20,000 students and 400 teachers annually. SURF is generating a $2 billion economic impact on South Dakota this decade alone, with the potential to create 1,200 jobs across the state. We are proud of our history, which includes Nobel Prize-winning research on this site, and we have a bright future with ongoing and planned experiments that will continue to inspire and push the boundaries of human knowledge for decades to come.
I have to get my cue from Matt that the live stream has started before I can start talking. Hello, welcome to our March edition of Deep Talks here at the Sanford Underground Research Facility, the Sanford Lab Homestake Visitor Center. My name is Mike Ray. I'm the Media Relations Manager at SURF. It's so great to see so many people here tonight because this talk is going to be awesome. I'm very excited that we have Dr. Stephen Sekula with us. If I said
Sekula,
that right?
yeah.
Sekula, okay, good. And his talk is, of course, To Catch a Dying Star, the astronomy of deep underground. We do need to thank all of the great sponsors who make this wonderful event happen each month and who provide the wonderful food and beverages that we have. And of course, that includes Crow Peak Brewing Company. They've been sponsoring this event almost since it started, and they're why we have free beer, which is totally awesome, thanks to Crow Peak Brewing Company. Of course, thanks to Edward Jones, financial advisor, as well, Chris Mitchell, RCS Construction, and Charles and Jolene Lichtenwaller. Let's give a quick thank you to all of those sponsors who make this wonderful event happen each year. Dr. Stephen Sekula is a physicist and research group manager at SNOLAB and professor of physics at Queen's University. He has a very, very long resume. There's no way I can fit it all in. I just want to hit a few highlights. He was a postdoctoral researcher at MIT and Ohio State University. He worked on the ATLAS experiment and the Large Hadron Collider over at CERN. And he served in many positions at Southern Methodist University in Dallas, Texas, including the physics department chair. He's also an author, so check out his work online as well. And without further ado, I'm going to pass it to Dr. Sekula for this evening's lecture. Thank you.
Thank you very much. Thank you. Thank you. So tonight I'm going to tell you a story in 4 parts. And in the first part, we're going to look at the death of a star. Then I'm going to take you to deep underground, the luckiest place on Earth. We're going to look at astronomically patient experiments that are attempting to predict the visible death of a star. And we're going to talk about how we can use those experiments to create an early warning system for these distant phenomena. So to begin, let's take a look at the death of a star, and let's unpack one of these events. So the story begins about 168,000 years ago, when what is known as a supergiant blue star entered its death phase. It had already been dying for some time, but it finally reached the end of the line. And it happened here in the Large Magellanic Cloud, which, despite its humble name, is actually a small satellite galaxy full of stars that orbits our own galaxy, the Milky Way. And specifically inside of the Large Magellanic Cloud, as we zoom in on it, right here, near this structure called the Tarantula Nebula, that's where the death occurred. And when it occurred, it was spectacular. Astronomers that saw the light from this explosion of this dead star could see it outshine the light from all of the other stars from that small satellite galaxy. And in fact, this phenomenon called a supernova, when it occurs in a galaxy for a brief time, for a period of weeks and months, that single exploded star will outshine the light of all the other stars in that host galaxy. This phenomenon is known as supernova 1987A. Because even though the star died 168,000 years ago, it took that time for the light to cross the gap between the Large Magellanic Cloud and our home solar system here in an unfashionable outer suburb of the Milky Way. Now, this turns out to have been the closest visible explosion of a star, and I'm putting a little star next to visible. I'll come back to that in a bit. Since 1604. Does anybody know what happened a few years after 1604? That's the great cosmic irony of all of this. I'll give you a hint. Something was invented. What was the thing that was invented? The telescope. Since the telescope was invented, there hasn't been a visible supernova in our own galaxy, which is just cruel. We're going to come back to that in a bit, okay? Now, its light arrived on February 23rd, 1987, but astronomers didn't see the light as it built up from the explosion. They only saw it after it became bright enough to notice, and that somebody then noticed, that there was a new star in that direction that hadn't been there before, and it was this thing. This is the result of a stellar death. And stellar death produces a lot of the atoms that, down the long chain of cosmic history, come to make up us and the planet that we reside on. But to understand that death, we have to understand stars. So let's do that. And one character I'm going to focus on tonight briefly in this is Dr. Cecilia Payne, who lived from 1900 to 1979. And if you've never read her biography, What Stars Are Made From, I highly recommend going and getting it. She was passionate about science from an early age. Her family encouraged this, but she grew up in England. And the truth was, at the time, for a woman, there was no way that she was going to get a job in science in the United Kingdom. And that's exactly what her professors told her. She was bright, she was promising, and unemployable, because that was the culture at the time there. So she was advised by her closest mentors to go to the United States, because there you can have a career. Now, it wasn't easy. She went to Harvard. Harvard didn't have an astronomy department at the time. But the supervisor of the Harvard Observatory, who had been scheming to create an astronomy department, recognized that he could build it on her brilliance. So she was the first graduate student and first graduate of the Harvard astronomy program, which did not exist prior to her being there. Now, that graduation is also a story fraught with peril, because what she did was she combined a massive data dump of astronomical information about stars that Harvard Observatory had been sitting on for years, but not really doing anything with. She combined it with the new science of quantum physics. She brought those two things together and realized that by bringing these two pieces of information together, you could actually figure out what stellar atmospheres are made from. And the original conclusion of her PhD thesis was that stars are primarily made from hydrogen atoms and helium atoms, and this conclusion was met with scorn. How could that be? That is not the primary stuff we find on Earth. There's very little hydrogen and very little helium on Earth. In fact, helium was discovered by finding it in the sun first, by doing astronomy. Iron, nickel, copper, this is the stuff that primarily makes up Earth. Calcium and other elements like that. But hydrogen and helium are very little. And so she was actually forced to change the conclusion of her PhD thesis, which many years later, when it was recognized she was correct, was also recognized as one of the greatest mistakes that those mentors had made. So what's the Earth made from? I'll make this easy for all of us. Earth is 98.8% Earth stuff. Okay, what is Earth stuff? It's mostly iron, oxygen, silicon, magnesium, sulfur, nickel, calcium, aluminum, and then the rest of it, including hydrogen and helium, which is a tiny part of the total, is just 1.2% of what makes up the Earth. But that stuff turns out to be star stuff, because stars are 98.7% hydrogen and helium. And they're only about 1.3% Earth stuff, iron, for example. Now, that doesn't sound very impressive, but if you take the iron content that's in our sun right now, you can make 2,000 Earths worth of iron from that. That iron is not being made in the sun actively. In fact, our sun should never really make iron. That iron's left over from the explosions of older stars whose debris was scattered into the Milky Way and eventually came to be collected into a new generation of stars, one of which is our sun. So here's a picture of our sun. It's a combination of different kinds of light, but it's made using light. And I just want to give you a sense of the scale of this. This is a medium-sized star. It's a middle-aged star. It's halfway through its life cycle. It's got about 5 billion years left before it enters its first gentle death phase. We'll come back to that. That blue dot, for scale on the same picture, is Earth. So if you just compared the diameters of these two things, that's our planet, and that's the sun we orbit. Now, we orbit really far from it so that you can block it with your thumb if you put your thumb up. It's about the same size as the moon. And hey, tonight there's a lunar eclipse, which if you're a night person, get up around what, midnight, 1 a.m., that's when it's going to peak, and go take a look. The moon will be red because the Earth will eclipse the sun from the moon's perspective, and the only light that will come through will be filtered through our atmosphere. And just like sunsets are red, only the red light makes it through the atmosphere and then illuminates the moon, which makes it look blood red. There's a lander on the moon right now that has a camera on it, and I don't know if they got the camera working, but it'll be the first time anyone has ever photographed an eclipse of the sun by the Earth from the moon's perspective, if that camera is working. So let's all cross our fingers and knock on something wooden and hope that that camera is working. Now, I'm not going to give a deep lesson in atoms here, but I want to introduce some basics because they're going to come back. The simplest atom, hydrogen, is made from a central nucleus, a single proton, a positively charged object, orbited by a single electron, a negatively charged object. Opposite charges attract, and that's what holds the structure together. Now, hydrogen has some cousins. If you slap a neutron onto that proton, then you make something called deuterium. Deuterium is stable on the lifetime of the universe. It was forged in the beginning of time, about 3 minutes after the universe came into existence. And it's also, again, orbited by one electron. And then there's tritium, which is the impish cousin of the hydrogen atom, because this one's unstable and doesn't live very long and is a great radioactive source for doing science with. Now, the reason I show this is because I want to show you the neutrons. The neutrons are like nuclear glue. So the minute I make helium, I need 2 protons. But like charges repel. Why do the protons stick together in the nucleus of a helium atom? And it's because there are also 2 neutrons in helium. So neutrons are nuclear glue. The protons want nothing to do with each other. The neutrons are like, hey, can't we all just kind of get along? And they glue it together. And helium is also stable on the lifetime of the universe. It's the second most abundant atom in the universe. Now, I'm showing you this because I'm going to show you some nuclear physics in a moment. Now, this is a cartoon. It is not to scale. The nucleus of an atom is 10,000 or 100,000 times smaller than the orbit of the electrons. So this is definitely just to give you a sense. Now, stars are about 75% hydrogen, about 24% helium, or thereabouts. So how do you make a star? You take a big cloud of hydrogen with some helium in it, and it starts to collapse under its own gravitational attraction. So it just starts to collapse in on itself. And when it collapses enough, when you get enough protons close enough to each other, some of those protons will begin to stick together, and they will fuse into deuterium. And in that reaction, they will spit off an electron, a fast electron, which is called a beta ray. And they will spit off an impish little cousin of the electron called the neutrino. So how many of you have siblings? I have a sibling. Okay, how many of you have younger siblings? Okay, great. Now, did you like it when your younger sibling wanted to follow you around, when you just wanted to go hang out with your friends? And I see some heads shaking. Yeah, I mean, I didn't have friends, so my sister didn't have that problem. But if I had friends, I wouldn't have wanted my sister around while they were there. She was the cool one in the family. So the neutrino is like the little sibling of the electron. Anytime an electron gets made like this, a little neutrino gets made too. And they're just a set. You can't break up the set. So there's the neutrino, and we're going to talk about neutrinos a lot. You fuse, you get energy. This fusion process continues, and eventually you make helium. This starts to cause the star to heat up, so it expands, okay? But the balance of the collapse of this gas cloud and the heat from the fusion is what ignites the star into existence. And so I have here like a little recipe reimagining something my grandmother would write down. You know, you apply some gravitational pressure, keep going. You know, eventually you start making neutrinos. The star is going to cool a little bit because those neutrinos will punch out of the star and leave. Keep compressing, keep it going. Eventually you're going to get the fusion process sustained, and you're going to start building up helium inside the star. Let's take a look at beta rays. And we're going to take a look at beta rays by looking at a rock from the Earth. So there's a couple of rocks from the Earth. And you'll notice that these wispy clouds keep appearing around this rock up here. The device that the rock is sitting in is known as a cloud chamber. There's an alcohol vapor inside of, it's a petri dish. That's just a plastic petri dish. A high school student and I built this last summer. It's all being cooled using off-the-shelf computer parts. And you can, in principle, make one of these for less than $300. and you can put a rock in it, and you can look and see if the rock gives off radiation. And this rock does. So you'll notice there are thick, short, wispy clouds, and then there's this one whopping great zinger of a cloud that shoots off here that's really long. And I'm going to freeze frame that for us. That is a beta ray. So that is a very fast-moving electron that got spat out from a nuclear reaction somewhere in the rock, probably very close to its surface. But everything we know about the last 100 years of nuclear physics says that when that beta ray got made, that little sibling, the neutrino, also got made. But I don't see another really good, distinct cloud in here, right? These are smudges on the Petri dish. I went back and really studied this in the image. These are just smudges. This is some of the felt that got stuck on the underside of the Petri dish. I didn't exactly clean this before I made this movie, okay? But you don't see another wispy line shooting out here someplace that would be the neutrino. And that's because neutrinos can punch through matter as if it's not even there. In fact, if I stacked up lead bricks until I basically got 1 year away at the speed of light, so if I stack bricks end to end to end to end to end, and I keep doing this, I don't know where I'm going to get all this lead from, but I keep stacking bricks, and I make a stack that is as long as it takes light to travel in 1 year. Light is the fastest thing in the universe. It goes 1 foot in a billionth of a second. I would still probably not make a neutrino passing through that lead actually hit the lead. So the neutrinos just pass through it like it's not even there. They'll pass through whole stars, they'll pass through whole planets, and you'll be lucky if any of them interact at all. That's the challenge of a neutrino. If you're going to use neutrinos to do things, they're great because they make it out of stars like our sun. But they're terrible because they'll pass through lead and not even stop. You have to be really lucky to catch one, or you have to be really smart. And that's the combination we're going for in this field. So this is just, again, to show you this complicated recipe for, this is one of the ways you can make a star. You start with 4 hydrogens, and through a long chain of fusion, you wind up with 1 helium atom at the end. And along the way, you spit out light. So this is where the heat of the star comes from. You spit out electrons. These things will go on to interact and also make energy. But you also spit out neutrinos. And the neutrinos will carry energy out of the star over time. And in principle, if you're clever enough, you can actually see those neutrinos. You could make an image, like an astronomical image of the sun in neutrinos. So here's the sun again in light. And here's an image of the sun using only neutrinos. This data was collected by an underground neutrino observatory in a mountain in Japan, the Kamioka mine. The detector is called Super Kamiokande. It is a successor to the original Kamiokande detector, and we're going to see Kamiokande 2, which was the second generation detector later. It is designed to catch some of the neutrinos that come from the sun. And over this period of about 22 years, it detected the sun using only neutrinos. Now, this is normally because the neutrinos are made in the heart of the sun. These should only be coming from the core. But this image is bigger than the sun would actually appear on the sky. And that's because it's really hard to point back to where the neutrinos came from. So 2 things to remember. 1, neutrinos are really hard to stop and take a picture of. And 2, the picture is fuzzy because even if you do get them to do something, you can't quite figure out what direction they were coming from. So it's a little bit like taking a picture out of focus on your camera phone. Yeah, I can see that the folks in the front row are in the photo, but I can't tell you anything about their features. I might even think you were sitting 1 seat to the right if the photo's blurry enough, right? And that's just the challenge of working with these little particles. Now, when the sun dies, it'll be a comparatively gentle death. Earth will not survive it. That's the bad news. But it will also not be an explosion. It will not be a supernova. It takes a much heavier star to die explosively. So let's look at a few promising candidates near the Earth. And some of these are very popular. I'm going to show you one that nobody talks about, but I think that's too bad, because it's just as far away as the one everybody talks about. And it's actually, I think it's scarier, and I'll show you why in a moment. So this star here, this is Antares. And let me go back here a second. This image is actually a telescope image of the surface of the star Antares. It is one of the only other stars in the Milky Way that we actually have a photograph of its surface. Our sun, that's pretty easy these days. But to take a picture of the surface of a star that's really far away, in this case, 700 years at the speed of light, is a really challenging thing. And the reason we're able to do this is, first, we can do it with radio waves. And radio waves are a little bit easier to work with here. And two, this star is bloated. It is in its death phase. And when stars die, they expand. Then they collapse. Then they expand. Then they collapse. You don't want to be a planet in the inner solar system of that star. So this is an artist's reconstruction of what the surface might look like in finer detail. And if you go out at night and you look in the direction of the star Antares, it's a red star. Some people will mistake it for Mars. It's a red star. Just know that it is the angriest emoji in the Milky Way, and it is watching you. So this is turbulence in its surface that creates these hot zones and these cold zones. And just, again, I want to illustrate how bad this is. That dot that you can barely see right there, that's our sun in size comparison to what Antares looks like now in its death phase. Let's look at another one. This is the one that gets all the headlines, and this is Betelgeuse, which is in the constellation Orion. It's the bright red star in the constellation Orion. It too is dying. And its surface has been simulated using state-of-the-art computational plasma simulations of these things. And it is this turbulent mess. And for scale reference, that would be the sun, but not to scale. That's the orbit of the Earth there, and that's the orbit of Jupiter. So if we were in a solar system with the star that was originally Betelgeuse, and we were in Betelgeuse's solar system now, Jupiter wouldn't exist anymore. It would have been consumed by the expansion of this star. And again, that's our sun. It's actually twice as small as it was before, but it's really hard to tell on this scale. So this one's twice as big as Antares. And both of these are primed to explode at some point. We just don't know when. And they're only 700 light years away, 700 years at the speed of light. And so we would like to kind of know when they go off that we should look in that direction to see something interesting in the light. And that's what neutrinos are going to give us. So I think this is a very fast thing here, but this is a few-year-old now state-of-the-art supercomputer simulation of the half-second in which a star finally collapses at the end of its life. The core heats up. Neutrinos get produced in huge numbers and come spewing out. They reheat the material in the star. Even though they don't like to interact that much, there are so many neutrinos, and the star is so dense when it collapses that they begin to reheat the star and blow it apart. Inside, the core collapses into something called a neutron star. So that's the neutron star forming deep in the core, okay? And now we're going out and we're watching these tracer particles showing the shock wave exploding out. Again, we're now 0.856 seconds after the star collapses for the final time. It is turbulent, it is uneven, it is a mess, and it took decades to be able to simulate this. And we can use information like this to think about ways that we can predict stellar death before it happens, before we can see it. Now, when supernova 1987A exploded, something remarkable happened. The neutrinos that cause that blast to occur, they get out first. So yeah, they get tangled up in the star as it dies, but they get out. The light from that explosion, it gets caught up in this mess of dead star atmosphere, all these particles whizzing around. Light likes to interact with all that stuff. So the light gets slowed down. It's like swimming in syrup for the light to get out. The neutrinos, it's like jogging on a nice still day through dead air. So the neutrinos get out first, and they get started on their cosmic journey. The light takes more time to get out of the explosion, so it gets slowed down and delayed. And so as a result of this, and people had known that this was a possibility, the blast wave of neutrinos from a supernova should arrive first on Earth, followed later by the light with some time delay. 99% of the energy of the explosion goes into making neutrinos. 1% of the energy goes into the light that the astronomers prize so much for trying to make sense of these explosions. If you want to understand supernovas, if you want to understand this kind of stellar death, you need to bring everybody to the table. You need neutrinos, you need light. The problem is neutrinos are hard to detect, and if you build an experiment on the surface of the Earth to try to see them, you will be swamped by the ambient noise of everyday life on the surface of the Earth. And I'm not talking about cars, I'm not talking about truck horns, I'm not talking about people chattering on the internet. I'm talking about the fact that the surface of the Earth is bathed in naturally occurring radiation. And that radiation gets into your neutrino detector and it causes it to light up. So you just have this noise, this constant noise of radiation lighting up your detector over and over again. You're not going to see the one neutrino every month or something that you're looking for. And when a supernova explosion occurs, that blast wave passes through the Earth in about 10 seconds, and a good experiment will see something like a dozen or 2 dozen neutrinos. That's it. So if you have all this other noise in your detector, you're not going to see this. This is why these telescopes that look for these neutrino signals have to be put under the Earth to shield us from the stuff that's raining down on us all the time, to quiet the noise so that we can have a hope of just seeing the neutrinos. And this is in fact what happened in supernova 1987A. It wasn't a prediction of the supernova, it was a post-supernova observation. 3 hours before the light from the supernova was observed, 3 different neutrino experiments scattered across the surface of the Earth all saw a pulse of neutrinos. And by a pulse, I mean they were used to seeing one every now and then, and combined, they saw 25 in 10 seconds. And just for the record, neutrinos interact so little, but there are so many of them passing through the Earth when this blast wave comes. This is kind of terrifying that suddenly an experiment that's used to seeing maybe one a week or one a month sees 25 or 10 in 10 seconds. That means something amazing has happened in the universe. This is Kamiokande 2, the 2nd generation experiment in that mine in Japan. For scale, there's a person. So it's a large tank of very pure water with light detectors inside, and when the neutrinos interact, the interactions give off light and they can detect the pattern. And they saw about 12 neutrino interactions in 10 seconds. Total, the 3 experiments saw 25. And it happened 3 hours before the light arrived. And this is when it occurred to everybody that a practical early warning system for supernovas was possible. And it could be done with neutrinos. So this is what supernova 1987A looks like today. The explosion is still spreading out. The inner explosion has met the stellar atmosphere that was sloughed off a long time ago, and that collision is leading to these beautiful rings from the supernova remnant. There's a fast-spinning neutron star down in the heart of that now. That's all that's left of the original star. And it taught us about this trick with neutrinos. So neutrino experiments benefit from going underground to be shielded by the planet so that you can quiet the noise and see neutrinos and see a bunch of them in, say, 10 seconds. Now, supernovas are expected to occur once every 60 years or so, give or take. So about once or twice a century, roughly. And when the neutrinos arrive, as I said, they do so in a 10-second window. So here's the challenge. You need a neutrino experiment to run for decades, and it's got to be up and running for the 1 10-second period that's interesting in that time. That is a huge challenge. How many things in your home run for decades and are up all the time so that they're ready at any moment to do what they're supposed to do? Yeah, I hear chuckling, right? I mean, I'm lucky if my car lasts 10 years, right? So, well, the way I drive it. So, all right. So, one thing I want to comment on here is I said visible supernova. The last visible supernova in the Milky Way galaxy was in 1604. This one was outside our galaxy, but kind of in the neighborhood. So what do you mean they happen every 60 years? I did the math. 1604 was a long time ago. It wasn't 60 years ago, right? Okay, well, that's a good point. And from that perspective alone, the Milky Way is overdue. Any moment now, a star is going to detonate. Well, we'll see that a star has detonated. It probably detonated a long time ago, but we should see it. Now, it's actually not that simple, because not all galactic supernovas are visible. If you look at the Milky Way, you'll notice there's places where there's lots of bright stars, and there's places where you don't see a lot of stars, and that's because there's a whole bunch of dust in the way. The Milky Way is filled with dust, and that dust blocks light. But we've learned to look through the dust using other kinds of light, ultraviolet light, X-rays, gamma rays, radio waves. And when we did that, we started noticing that there were supernova corpses around the sky that were recent but unseen. So there are two supernovas, one that's estimated to have occurred in 1680, so not long after the invention of the telescope, but it wasn't visible to the human eye, so that's nice. And then one that occurred sometime in the 1800s, let's call it 1868, that's kind of the average estimate. But it was, again, obscured. Nobody on Earth saw it. There's no report of anyone seeing this. And it was behind dust. So that seems to have been enough to block the visible light. So we need all ways of seeing a supernova if we're going to be ready for the next one. It's possible, in fact, to detect a supernova without seeing the light from it, using just neutrinos, and then taking these other things like ultraviolet light and using them as your tool to probe the supernova. So let's go underground. Let's go under the luckiest place on Earth. And you'll see why I call it that in a moment. So to get to where I work, around Greater Sudbury in Ontario, Canada, you have to take few planes. It's not one, this makes it look really, thank you Google Flights for making it look like there's a direct flight to Sudbury. There is not. Okay. All right, so Rapid City, the team that I came with, our route was Sudbury, Toronto, Denver, Rapid City. So we're just going to reverse that to go back. So it's about 8 hours on a plane, or several planes, okay? Let's zoom in. Let's take a look at this region. So this region is known in the Ojibwe dialect. The Ojibwe have settled there about 9,000 to 10,000 years ago. And this land is known as the place where three roads meet. There are many ways you can read that. But these days, you have indigenous people, European people, and a growing Asian population there. So that's kind of three roads that meet in what is also known as Greater or Sudbury Grand. And you also have three major roads that meet there, so that's literal. You also have art and science and industry meeting in this place. And the lab I work at is an intersection of science and industry and growingly art and culture. So why do you think this is the luckiest place on Earth? Can anybody see why Sudbury is lucky? And let me know if you need a hint. Did anyone get excited by the recent news that there was a near-Earth object that may have a greater chance of hitting the Earth sometime in like the early 2030s? Okay, I see some nodding heads. Okay, so that's a clue. So do you see any evidence that Sudbury might have been hit by a meteor at some point? I see some pointing. What are we pointing at? We're pointing at something here. What are we pointing at? Shout it out. The lake. Yeah. That looks suspiciously like a crater lake, because it is a crater lake. That crater lake was formed a few 100 million years ago by a strike. Okay, so we'll go ahead and highlight that. But that's not the interesting one. The interesting one is the one that your eyes weren't drawn to, and that's this monster. Because Sudbury has been struck twice in nearly the same place by meteor impacts. This one, this big one, was 1.9 billion years ago, when at best there was sort of simple multicellular life running around on Earth. So if there was a mass extinction, it was a mass extinction of bacteria, or something like bacteria. The continents were also one continent back then, so it was a very different planet. This impact was enough that if there had been things like dinosaurs running around on Earth, they would have been wiped out. It was a massive impactor event. And you'll notice there's a ring of rock here. It's distorted now. When the continents shifted and split, it stretched out the crater. The crater was round, but it's not round anymore because the Earth moves. The surface of the Earth is fluid. This thing here is known as the valley. A lot of people say, oh, I live out in the valley. The valley is the center of the impact crater. The edge of the impact crater is ringed by these high ridges here. And that is not coincidentally where the mines are located, because this impact was so fierce that it punched through the crust and upwelled the mantle material up into the atmosphere and then down onto the crust, exposing huge veins of things like nickel, copper, and gold that wouldn't have normally been in the crust in this quantity, but were ripped up from the mantle by this impact. And so that's why I consider Sudbury, for many reasons, to be the luckiest place on Earth. I mean, if you're feeling lucky, lightning literally struck twice here, okay? And we benefit from that. In the long chain of human history down the road, once humans got here, we benefited from this. It shaped the land. It created a valley. It created a ring of rock around the valley. It's a very protected area. 300 beautiful lakes in this area. It's just a gorgeous natural area. Industry arose in the 1800s with the discovery of these exposed ore bodies that at first could be accessed by, say, open pit mining, but eventually they went deeper. I'm going to focus on the Creighton mine. The Creighton mine is where SNOLAB is located, and it goes down about 9,000 feet now. 9,000 feet is where the active mining is going. So the open pit has recently been reopened, but a lot of the active mining is going on in the deep. Now, I want to acknowledge here that SNOLAB is located on traditional territories that were covered by the Robinson-Huron Treaty of 1850. And it is shared by those indigenous people that came about 10,000 years ago to this particular land, now known as the Atikameksheng Anishinaabe First Nation. And they're part of the larger Anishinaabe nation. And one of the things that we always reflect on is that all of us as human beings are in a relationship with this land. We are its caretakers. Sudbury is still reeling from the industrialization, from the smelting of nickel ore and so forth that led to the acid rain problem that many of you may be familiar with. And a lot of this has been revitalized in decades. It's a massive undertaking, but it takes caretakers. And recognizing that we are caretakers along with all of those who've been on the land before us is an important part of all of this for us. So let's take a look at why you want to go underground. So SNOLAB is 6,800 feet underground. SURF is 4,850 feet underground. We are sister laboratories, and we are joined by this desire to shield ourselves from the noise of the surface world. So this is a chart. Vertical is more noise from radiation at the top, less noise from radiation at the bottom. The horizontal axis is shallower on the left, deeper on the right. And what do you notice? As you go deeper, as you build capabilities in mountains, the red triangle, so you can drive horizontally into these mountain facilities. Or if you dig into the flat earth, so mines, shafts, tunnels, and use a cage to get down, you can get under the noise. You can get deeper and deeper and quieter, so you have a hope of seeing rare things like neutrinos. So here is the SURF laboratory. There's a sister laboratory in France known as the Modane Laboratory, which I had the privilege of visiting a couple of years ago. And they are roughly at the same effective radiation shielding level, although Modane has to be deeper than Sanford to do this. Why? Because it's under a mountain, and a mountain looks like this. So your best shielding is straight above your head, and then you're weak in all other directions from the sides. When you're in a flat underground laboratory like this one, when you go under the surface of the earth, so the cost you pay is you can't drive in easily anymore, but your weakest point is straight overhead, and you're stronger now to the sides. That's the trade-off in all of this, accessibility versus shielding. And so this is sort of the race, right? So here's SNOLAB, the lab I work at. It's at 6,800 feet of rock, norite rock above its head. And this is another sister laboratory, Jinping in China, under a mountain. It has to be deeper, but it actually doesn't quite get as much shielding as we do at a shallower depth. So this is the competition. Underground labs vying for capabilities, vying for interesting experiments, but also working together to solve difficult problems. And to point out here, SNOLAB enjoys a reduction of 50 million times over the ambient surface radiation levels by going this deep. So it comes at a cost, but it has a huge benefit associated with it. So let's take a journey. So this is the surface building at SNOLAB. This is one of the parking lots. This is a lovely foggy day when I took this picture. And this is it's a pretty standard office building. It's got some laboratory facilities in it, but it's otherwise a pretty standard office building. When we want to go to the underground lab, we put on our personal protective equipment and we walk. It's a short 2-minute walk on marked walkways over to the head frame of the Creighton Mine No. 9 shaft. This is the only active cage anymore that's operating at the Creighton Mine site. There's the head frame. And so we go down to the cage and we load on in the morning. The standard cage for SNOLAB is 6:30 in the morning. And the cage times are pretty similar here at SURF based on everything I've learned so far. So we all kind of suffer the same way. It's great. This is our cage. It holds 40 people per deck, and it has 2 decks. It's a double-decker cage. So you stand shoulder to shoulder with your backs to the wall on the left and your backs to the other wall on the right. And if you're not smelling what your neighbor had for breakfast, you're not close enough, pack in more, okay? I know, it is awful, but 6:30 in the morning, everyone's suffering. So now, to give you a sense of scale here, so here is the No. 9 shaft, and then we're going to take the cage down to the 6,800-foot level, and then our job's not done because then we have a walk of about 1¼ miles in horizontal tunnels, drifts, over to the actual SNOLAB. So the surface building is roughly here, but about 1¼ mile away under the ground is actually where SNOLAB is located. So it's a walk in and it's a walk out. So let's take a look at what that journey would look like. So again, we start on the surface building, bright and early. It's never that bright in the morning at 6:30 in the morning, even in the summer. And so what we're going to do is we're going to walk over, we do our briefing, we get our clothes on, we get in the cage. This is a fast cage ride. 6,800 feet, 4 minutes. Time is money. It's an active nickel mine. Get to 6,800 foot. Because the miners have another 45-minute to an hour drive down switchbacks to get to the operating level of the mine. We walk in, we wash off our boots. We want to get all the mine dust off of that equipment as much as possible. We shed our outer protective clothing. We go into respective men's and women's dries. You then shower. You are the problem in SNOLAB. If you bring any mine dust in and you touch a sensitive detector, you ruin the experiment. Not because that dust is super radioactive, it's just radioactive for our really sensitive experiments. We are the problem that we have to protect our experiments from in SNOLAB. We don clean room gear. We go inside. This is the lunchroom. It's probably one of the least clean areas inside. But the entire lab, 54,000 square feet of lab space underground, is a class 2000 clean room space. Once you're in a clean room. It's the cleanest space you'll probably ever work in, except for a few places in SNOLAB that are even cleaner. Everything is hand cleaned that is brought into the laboratory to prevent dust contamination from getting into the lab. We have many experiments. This is the control room for the original Sudbury Neutrino Observatory. It's the reason the lab exists in the first place. And this experiment shared the 2015 Nobel Prize with Super Kamiokande for the discovery that the neutrino can change from one of its kinds to another, and that this implies that it has mass, it has substance. We make our own utilities underground. We make ultra-pure water. We have to filter our air. We have to reduce radon gas from the air. Just like a basement, you get radon underground, and radon will ruin an experiment. You got to get the radon out. We have these ultra-clean spaces. So this is a phone booth-sized inner clean room where they work on quantum computers and other sensitive instruments going into facilities. We have underground biology to answer questions like, is there such a thing as too little radiation for living organisms? Hint, the answer may be yes. There's a sweet spot for living organisms because of how we evolved on the surface of the Earth, and there's radiation everywhere. You take that away, you stress the organism. It can actually get less healthy as a result. We have vast spaces and we have small spaces. So this is known as the Cube Hall, and it's home to multiple large experiments, and we're hoping to put more in there as well. So let's take a look at SNOLAB and its layout. So this is all mine drifts here. Where you enter the clean space is actually in this area here. So we have the lunchroom here. And then if you walk out into the corridor, you head left, you go to the old Sudbury Neutrino experiment area. There's now a new experiment there, SNO+, the next generation experiment that's trying to answer different questions about the neutrino. You go this way, you go to the new lab space, so-called ladder labs, the cryo pit, and the cube hall. And just to give you a sense, the largest cavern we have here is about 90 feet from floor to ceiling. That's currently filled with water, so it's not very exciting. You can't go see it. But these spaces, the cryo pit and the cube hall, the cryo pit is about 60 feet tall. And it's a big space and can hold multiple experiments. It may hold one big one day. But this is your job, underground. Walk around, work on your experiments. So again, original clean space. This is the more recently constructed clean space. This is now what we call SNOLAB. And again, it's 1.25 miles underground. This is a picture of the Sudbury Neutrino Observatory when it was being constructed in that cavern before it was filled with water. And again, those are people for reference. This sphere here made from acrylic is the heart of the experiment. It's a neutrino detector, and it is about 12 meters, so it's about 36 feet in diameter. It is huge. And it looks, I love this because it looks like they're holding it up. They're holding up the frame. I love that picture. It's beautiful, absolutely beautiful. But this is, of course, all suspended from up above and from the sides. So this is one of our neutrino detectors that's operating now at SNOLAB, and it is part of an early warning network. But the one I'm going to show you is HALO, whose motto is astronomically patient. And HALO was inexpensive. It was designed to be up almost all the time and to be ready for that 10 seconds every 30 to 60 to 100 years. So let's take a look at that. So if we come in from the lunchroom and we enter into the formal clean lab space and we walk this drift here, we come to an unfinished drift here known as the HALO stub. And in principle, one day we could punch through this and build more lab space over here. There are plans for that. There just needs to be a motivation to do it. All right, so let's go there. So this is the corridor that you would walk down. This is what the clean lab looks like on the inside. I mean, it looks like an industrial site. The only difference is that that's concrete that's sprayed on, hand troweled, and then painted, known as shotcrete. So this used to look like a normal mine drift, but then the walls were put in and treated, and this is what it looks like now. It's absolutely pristine. All of this has to be hand cleaned once a day. All 54,000 square feet is cleaned by a team of cleaners once a day. If you do the estimate, the cleaning staff at SNOLAB do the equivalent of cleaning Vatican City in its entirety 5 times every year by hand. That's, however, how our science can proceed. That cleanliness is the crown jewel of this facility. This is HALO, and it's got some key features. Green tubes. That's it. It's made of 2 things. Now, it's a little bit more complicated than that. We're going to talk about each of those pieces in a second here. But it's a big stack of green and tubes. So let's break it down. The green is lead. It doesn't look like lead because that's what lead normally looks like in its regular state. It's lead that's been painted with a special paint that's low radioactivity, and it prevents nasty lead compounds from forming that can aerosolize the lead, and humans shouldn't breathe that in. So this makes the lead inert by painting it this green color. And those bricks are shaped specially to hold the tubes inside of them. And as I said earlier, one neutrino can fly through a light year, a distance equal to the distance light travels in 1 year, and not hit anything. The lead was actually recycled. It was recycled from a cosmic ray radiation detector in Chalk River, Ontario, just down the road from Sudbury. I have an old photo of the lead bricks for the portable version of this detector, and they look exactly like these funny little cupped hand shapes that the lead bricks are shaped into in lead. So we just inherited that from this facility. And there you can see more closely that sort of cupped hand shape of the 2 halves of the lead bricks that come together, and then they're stacked in rows that go about 8 feet back into the detector. Now the tubes are also a recycling program. These tubes came from the original Sudbury Neutrino Observatory. When they weren't needed there anymore, they were decommissioned. And then later down the road, they were recommissioned to be the detectors for this experiment, the Helium and Lead Observatory, or HALO. So the neutrinos will strike the lead, and when they do that, they spit out neutrons. The neutrons bounce around in the lead. They go about 1/2 yard in any direction. And then they're captured by the gas inside these tubes. And when they're captured, they give off an electronic pulse. That's how we know that something has happened in HALO. And as I said, the tubes are recycled. And HALO is truly, in every sense of the word, a detector of opportunity. It was opportunistically constructed from things that nobody needed anymore, and it is waiting for this singular opportunity to be an early warning system for a galactic supernova. Now, it has to be up all the time. That's impossible, but the team on HALO and the design of HALO is pretty good. So we had a rocky start like any experiment, but basically for about the last 7 or 8 years, we have managed better than 99% uptime for this experiment. That means that out of 365 days a year, HALO is fully on and waiting for a supernova for at least 361 of those days. Now, all anyone's going to remember is if you missed the 10 seconds that mattered. But you got to start somewhere. Most experiments in this field would beg for uptime this high. This is considered gold standard uptime, and it has to do with an inexpensive design with lots of redundancies in it, so if one thing fails, another thing kicks in and takes over. So let's think about this now as a distant early warning system. We have the Helium and Lead Observatory is one of many neutrino detectors that are waiting patiently for a supernova to go off in our Milky Way galaxy. And there is a computerized network of these neutrino observatories called SNOOS, which may be what you're doing right now, depending on how this lecture is going, but also stands for the Supernova Early Warning System, SNOOS. Now, candidate stars. I showed you Antares. I showed you Betelgeuse. Is there anything closer? Our stellar neighborhood consists of something like the 25 light years around our sun. And there's some pretty awesome stars. I really like Sirius. Sirius is the bright star in the summer that's right overhead, big bright blue right over your head. Can't miss it. It's only 8 years at the speed of light away from Earth. It is a big blue giant star. The dog days of summer, that old phrase, that actually comes from an old belief that Sirius caused the hot days of summer because it was right overhead in the summer and was helping the sun heat the Earth. It's too far away to do that, but it's cute. So Sirius is known as the dog star, okay? So this is where dog days of summer comes from. Now, it too one day should detonate as a supernova, but it's not in its death phase yet. It's still very much in its sort of normal period of existence like our sun is. There's really nothing else in our immediate stellar neighborhood that's going to go. And so we're really looking to things like Antares and Betelgeuse. So just to give you a sense of scale, HALO alone could see a supernova as far out as about half the diameter of the Milky Way. It's not the whole Milky Way, but I'll take half over nothing. The Milky Way in total is about 100,000 years at the speed of light across. So when you see things like stars on the other side of the Milky Way, you're not seeing them as they exist now. You're seeing them as they existed 100,000 years ago, and the light is only getting to us now. We don't even know if those stars are still there. And that's the exciting part of all this. This is why we need an early warning system. We need something that gets here before the light does. So again, Betelgeuse, 700 light years in one direction, part of the Orion constellation. Antares, the angriest emoji in our neighborhood, 700 light years in another direction. It's exciting times. We don't know enough about stellar physics to know when they're going to go. We just know that when stars get to this phase, it ain't good. And the end is pretty much determined by nuclear physics, and it's brutal. So SNOOS assembles a whole bunch of neutrino detectors. So there's SNOLAB, the NOVA detector in Ash River. This is SURF, which is home to 2 experiments I'll show you in a moment that are capable of seeing supernova neutrinos. IceCube at the South Pole. They're scattered all over the place here. So we have global coverage on multiple sides of the planet, and that's good because the neutrinos that come from one side of the Earth will arrive at those experiments first, and then they'll arrive at the experiments on the other side of the Earth a little bit later. And global positioning systems and clocks are so good now that we can tell the difference between arriving on one side of the Earth and arriving on the other side of the Earth, even though neutrinos are moving really fast. So the neutrino observatories are ganged together through the SNOOS network, and if the conditions are met that multiple experiments report we think we see a supernova, a bulletin is issued. That bullet, I should show you the experiments here. So we have LZ, I'm in America now, LZ, and that's one experiment that's capable of detecting supernova neutrino bursts. And then what's being constructed now is the Deep Underground Neutrino Experiment, or DUNE. That is massive, and it will be a huge contribution to supernova neutrino detection. This is going to be a fantastic addition to SNOOS when it's completed. So, a bulletin goes out, and there are professional and private observatories across the globe. These are the red and purple dots. They get the bulletin, and the early warning system tells the astronomers, we think the neutrino burst came from this direction. Look here. Because without that information, the astronomers don't know where to look. Supernova could be over there. Supernova could be over there. Supernova could be over there. That's a lot of stars to cover. You're not going to be able to cover all of them. But if you know you need to look in this patch of the sky over here, enough observatories looking, one of them is bound to see the one star that blows and catch the light as early as possible to understand stellar death as early as possible when it happens. And if you want to sign up for the alerts, get out your phone right now, hurry up. I'm sure we can make the slides available. You can also search for SNOOS, Supernova Early Warning System, and you can sign up to get the alerts. Now, the original SNOOS was set up so that it allows for false positives to happen, but not more than 4 per year from any experiment. But the chance that 2 experiments give 2 false positives at the same time is really small. 3 is even smaller, 4 is ridiculously small. So they don't send out bulletins very often. You have to have a pretty big coincidence that hasn't got anything to do with a supernova to get an alert. So this may be the quietest mailing list you ever join, except for 10 seconds at some point in the future, okay? And so this is just an animation showing you, so if Betelgeuse exploded and the Earth was turned in just the right way, the first experiment that would see the burst might be the KM3-net detector in the Mediterranean, followed quickly by this detector in Italy, LZ in Surf, NOVA in Minnesota, Panda X in China, IceCube at the South Pole, Super Kamiokande, and CamLand, they're both in Japan. So the blast wave of neutrinos, the time difference between the first detection and the last detection is just shy of 0.03 seconds. Everything's got to work, and it's got to work at the right time. But we're ready for this, and we are very patient. So, in summary, the death of a star results in 99% of the energy of the star going into neutrinos. You want to understand stellar death? You need to look at stellar death and neutrinos. But observing the fullness of that requires very sensitive detectors deep underground. And two of those are currently in SNOLAB, the luckiest place on Earth in Sudbury. That lab is also home to the SNO Plus and the HALO experiments, both of which are trying to be as astronomically patient as possible, but there will be more in the future. There's an effort underway to grow the supernova capability at all of these labs, including SNOLAB. But neutrino observatories in general across the globe are linked into this early warning system to be ready for this. So if you've enjoyed this presentation tonight, I strongly encourage you to connect with SNOLAB as a whole through social media. It's always SNOLAB Science. Pick your favorite platform. It's very likely to be there. They're even on Mastodon. All right. I have big thanks to lots of people from HALO, to Donald D. Clayton, the famous astronomer whose biography, Catch a Falling Star, was the inspiration for the title of this talk. Many students who've done fantastic work on HALO over the years, including Rachel. Where is she? Hey, Rachel. Excellent, excellent. I haven't read your thesis, which is why you're not on the list, but we're going to fix that. Okay. If you like the storytelling I've done tonight, I really like science. I see it as an act of evidence-based storytelling. And if you've enjoyed that, I do have this hobby as a writer. I've co-authored a book for the general public called Reality on the Shadows that talks about everything from the discovery of the Higgs particle to the fate of the cosmos. And I wrote that with Jim Gates, and who's an excellent mathematical physicist, and Frank Blitzer, who sadly now has passed away. He worked on the Apollo moon landing missions. He co-developed the guidance system for the capsules to get them from the Earth to the moon. This book answers the question: a mathematical physicist, an experimental physicist, and a rocket scientist walk into a bar. You figure out the punchline at that point. If you want to listen to Chapter 7, A Sky of Shadows, which talks about dark matter and the expansion of the universe, you can grab that on YouTube. That's free. And I've started a series of books for university students who have taken their first physics courses in university and have forgotten why they loved physics in the first place because they got really beat up. I believe that with introductory physics at the university level, you can unlock the entire universe. You don't need to wait 4 years to do that. So these books are volume 1 for the general audience. Anybody can read them. Volume 2 for the university student that wants to see why their training will not go to waste. And I've got another one coming, Light in the Dark Cosmos, which talks about dark matter and the fate of the universe, coming this year, if my publisher is kind to me. So that's it. Let's go catch a dying star together. All right?
Dr. Sekula, we want to thank you so much for coming out tonight. We have a little parting gift for you, which is actually a piece of a picture of surf made from a frame that came from the Yates shaft. So this is wood from the Yates shaft as well. There's an envelope here. Thank you so much.
Thank you very much. This is fantastic. Wow. Can I just keep the wood? No. I love pieces of things. I like. There's nothing like more special than holding a piece of something in your hand, like a mine or a laboratory experiment or something like that. This is fantastic.
Thank you so much for coming.
And I have something for you all as well. Hey, Jarrett, can you come up? Where's Jarrett? I saw him. Yeah, come on up. So my spouse and I co-authored a textbook on hunting for dark matter, and SURF does incredible work through its dark matter search program. And this is for the whole lab, so you have to share. Okay, so make sure the students get this. It's to help enable discovery of dark matter. So, yeah. And it's signed. So, yeah. Yeah.
And we're right at 7 o'clock. We usually try to end on time. I do want to say that folks who want to stick around and chat, ask questions, feel free to do that. We can be here for a little while longer.
I'm happy to do that. Yep.
So thank you all for coming out. Our next Deep Talks, I believe, is going to be April 22nd, 23rd, right in there. We're going to cover the topic of surf. And it's our annual talk about all the awesome things happening at SURF. More on that TBA. So stay tuned for that, and we hope to see you all back in April for that event. Thank you all for coming out. Wonderful evening, wonderful talk. Stick around if you have some questions.
Please. Yep. Thank you.